Okay, determine the moon phase for each diagram. Anytime you have a moon phase problem, first thing you want to do is go find the new moon. The new moon is always located between the sun and the earth. And the moon, of course, travels counterclockwise. So then the moon phase right here would be the first quarter, which means that this phase all the way from here until the full moon is going to be the waxing gibbous. Over here we have our new moon would be located right here. This is the way that the moon would revolve around the earth. This would be our full moon right here. So the phase following the full moon is the waning gibbous. Okay, label the moon phase on the left. Shaded the moon phase on the right, to the right, to show the phase after the number of days indicated. Label the phase you calculated or drawn. All right, so this is going to be the new moon. 7 days later, the new moon becomes the first quarter. Okay, so this is the new moon. 7 days, it will become a first quarter moon. And a first quarter moon, the light is on the right. And so we're going to shade in the left. And this is the first quarter moon. That's just blank. Okay, so then over here we have the first quarter moon. The light's on the right. That's a first quarter. In 14 days, the first quarter will become a last or third quarter moon. And the last or third quarter moon, the light is on the left, so we're going to shade in the right side.
Okay, guys, tides. We all knew that the gravitational pull of the moon does pull on the water from the earth, creating tides. On certain moons, when it all lines up nicely, we have these special tides. So spring tides. Spring tides are very large tides. These are the largest high tides and the smallest, here the smallest low tides. So they occur during a new moon or a full moon, and that is right here when they're in a nice straight line. So this is a full moon. This would be the new moon right here, because you've got both the moon and the sun pulling in one nice straight plane or direction. Spring tides result in the highest high tides. And where's all that water coming from? Well, it's coming from the low tides. So this would be, pulls it from the low tides, making the low tides even lower. Neap tides occur when there is a first quarter. I'm going to just put Q for quarter, or a third quarter moon. That's when they have the least tidal variance. What does that mean? That the difference between the high tide and the low tide would be very small. So remember when we were talking, when we did that thing like that, and then this one right here, and then these over here, the small ones, these would be our neap tides here. That would be a little neap tide. It's a small variance between our high tide and our low tide, whereas these over here would be my spring tides in here. The very large high tides and a very low tide. And again, this would be a spring tide over here. So spring tides have a straight line, and neap tides have a right angle, or are perpendicular, whether it's this way or if it's the first quarter this way. Okay, so this is the rotation of the earth. First of all, the rotation of the earth creates, what does that do? Rotation means that it's going around. It's another word for spinning. Please make sure you know the difference between rotation and revolution. But the spinning on its axis creates day and night. If we are facing the sun, we've got day as it turns at 24 hours in a day, then if we're on the other side, it's nighttime. The 23.5 degree tilt of the earth as it revolves around the sun creates seasons. So two things, it's the tilt and the revolution. So we know that rotation causes day and night, the revolution and the tilt cause seasons. Summer occurs in the northern hemisphere when the North Pole, okay, here's the northern hemisphere right here, that's the top, okay, the top part up here. This is the northern, this is the southern, northern, southern. So summer occurs in the northern hemisphere when the North Pole is pointed or tilted towards the sun. So towards the sun. So this right here is going to be my summer in my northern hemisphere. It is winter when the North Pole is pointed away from the sun. So this kind of is tilted away from the sun. This over here is going to be winter. Now, what this does is this causes more hours of daylight or less hours of daylight. So we all know that in the summer we have a lot more hours of daylight, in the winter very few hours of daylight. So that definitely comes into play when we're talking temperature. In March and September, the North Pole is neither pointed towards or away from the sun, and the Earth, so the day and night hours are equal. So that you can really see right here really well. Not so much on this one right here because we can't see the part that's lit up on that side. The Earth rotates and revolves, just like everything basically. It's counterclockwise. The 23.5 degree tilt is the reason for the seasons. I always say Michael Jordan or and a half or LeBron James and a half.
Okay, to the left is Hubble's classification of galaxies. Name the three types of galaxies. Well, of course, we have the spiral galaxy. We have the elliptical. And we have the irregular. Which category of galaxy do we live? Of course, we live in the spiral galaxy. I always say it kind of looks like an octopus twirling. What is the name of our galaxy? It is the Milky Way. Yes. So real quick, just a reminder, spiral is going to be, it's going to have the arms. It kind of looks like this. Elliptical is going to be kind of egg or football shaped. It's going to look like that. And then irregular is pretty much anything that doesn't fit into those two categories. Where do we find our solar system, the Milky Way, in our galaxy? It's on the edge of one arm. So if this is the Milky Way galaxy, here we have the arms going around like that. Our galaxy, our Milky Way, would be located on the edge of one of the arms. So that would be the Milky Way. Thank you. Sorry. That would be our galaxy. That would be the sun. The whole thing is the Milky Way. Our sun is a medium sized star. The sun is the closest star to Earth. It is the source of all energy on the Earth. The sun provides all of our energy because it is the, again, closest, not the hottest, not the brightest, but the closest star to Earth. A blank is a cloud of gas and dust in space where stars are born. That is a nebula. A nebula is a cloud of gas and dust in space where stars are born. A star's age can be determined by using the HR diagram to compare the star's temperature and luminosity. Luminosity is just another word for brightness, which has to do with the star size. Depending, stars spend most of their life cycle within the main sequence. Of the HR diagram, which is this area right here, that's the main sequence. Our sun is about halfway through its cycle and a main sequence star. So our sun is somewhere around this area right here, It's a medium-sized star. It's got about medium temperature. It's got medium luminosity. Its luminosity is actually 1. We compare other stars' luminosity to the sun. What is measured? Now we're talking about the HR diagram over here. What is measured on the y-axis? The y-axis runs along there, and it is luminosity or brightness. The higher up in the diagram, the brighter the stars are, the lower they are down here, the dimmer they are. On the x-axis here, we have temperature. Temperature is measured on the x-axis. Name a very hot, very bright star. Very hot, very bright star are going to be your supergiants up here. I can't really read that. The HR diagram on here is a little bit fuzzy. So a very hot, very bright star. Rigel. Rigel is located somewhere over here. That's one of the very hot, very bright stars. A very bright, very cool star is going to be located in this area. It's going to be your red giants. And Betelgeuse is one of those that's in that area. Name a star that is bright in spectral class B. Again, Rigel is one of those. Name a star that is about 6,000 K and has a luminosity of 1. That is our sun. And it is a main sequence. Okay, wavelengths travel through the Earth's atmosphere with varying frequencies. What wavelength in the image above have a measured frequency of about 10 to the 14? 10 to the 14 is going to be right in this area right here, and that's going to be your visible light. That's the light that we can see with our eyes. Objects in space that are redshifted are moving away from us. Think about red, danger, move away. So anything that is redshifting is moving away. This right here is an example. You can see this object is right here. The first time that they measured it, moved a little bit over and a little bit over, so it's moving toward the red end of the spectrum. So this is a red shift showing the object that they're focusing on, that they're looking at, is moving away. Objects that are blue shifting, which means that in 1 year they measure it, it's going to be, if the object was here the first year they measured it, moved here and then moved here, then that's going to be shifting towards the blue, which means it is moving toward us.